Hello and welcome to section 21, second order circuits. So we're going to be introducing the equations that we use to solve second order circuits in this video. So a second order circuit is one that has two energy storage elements. So previously we only had one element, but now we can have capacitors, inductors, two of them, one of each. So the most common type are these two RLC circuits. They'll either be in series or they'll be in parallel, and there's other variations of this. You can also have circuits with two inductors or two capacitors if you orient, say you put a resistor or something between there such that you can't combine the capacitors or the resistors. So the important thing is they will have two energy storage elements. And because of that, we will get a second order linear differential equation that will look something like the following. So it'll be a second derivative. I'll write x here. This x can be v or I, depending on what you're solving, plus some constant a1, and then the first derivative of x, again x can be v or I, and then plus some a naught x. And this will all be equal to some g of t like we had last time. So this will be our right hand side is what I'll refer to it a lot of times. This is where our forcing functions and constants go. So it'll look like this, and then we're going to go have to solve it for x or v or I or whatever. And so we're going to generic form that says that when I solve these type of equations, these are second order linear, they're going to take the form x particular plus x natural. So that's the same as what we saw before. Where again, if you kind of sketch something out, these are going to have a bit of a bounce to them, but eventually they'll hit this line here. And this is our x particular. This is the steady state where it's going to get to, and then this bounciness is caused by this natural response. So eventually, after a long time, it'll reach this particular response, and it'll just stay there, and this natural response will be gone. Well, theoretically, if your circuit's stable, it'll be gone. If your circuit's unstable, then it'll just bounce. A good analogy would be a spring with no resistance. It would just keep bouncing forever. But most springs have air resistance of some type. Alright, so if I wanted to find x natural, if you remember we had AE to the S1T, well that's only for first order circuits. We are no longer going to use this. But it's going to look similar. So let's see what it's going to look like. So if I use the same trick, d dt equal to s, we'll sub in that for this equation, then I will get s squared x, so I'm just subbing in this up here, plus a1 times s times x plus a naught times s equal to, and so generally what we're going to do with the right hand side for this is we're going to set this equal to 0 because we're just trying to find the natural response, which is the unforced response, so there should be no forcing function. Oops, this should be an x, not an s. Sorry about that. Your x's go away, and this simplifies down to s squared plus a1 s plus a naught equal to 0. Hopefully you see that as the quadratic equation. Sorry about keeping that stuff up. I forgot to take that off. So that's the quadratic equation. So you can solve that however you want, but I'm going to prefer just to use the quadratic equation here. But if you want to try to factor it out, go for it. So this is the negative b plus or minus square root of b squared, so on and so forth. With our constants here, it'll look like minus a1. So you don't have to use this. You can just use your b, abc that you're used to if you want to. a1 squared minus 4a naught all over 2. So notice that our leading coefficient here is 1. Just like we did before, we want to get our leading coefficient to be at 1 over here. So that's standard form. So you'll do that, and you'll get two roots, S1 and S2. S1 and S2 can take three different forms. So they could be real and distinct. So for instance, the example that I give you in the handout is S1 is -2 and S2 is -4. So they would be real, they would be distinct. Distinct meaning they're different and they're real. There's no imaginary term. You can get imaginary numbers out of here. It's fine if you do. So what that means is that we are overdamped. So we will eventually stabilize here. We'll actually we'll get there too quickly. We're probably actually going to undershoot the curve, so what's going to happen in an overdamped case. So we'll stabilize, but we'll stabilize slowly. So you can think of it like you have too much shock absorber. So like you hit the bump and it doesn't quite rebound back fast enough. So that takes the form. So then our X, I'll use X. X natural will be AE to the S1T. Hey, there's our friend. Plus AE to the S2T. So now hopefully you see why we've been using S1. Because there's an S2. We get second order. Alright. Now, what if they're the same thing? What if I have an S1 is -2 and an S2 is -2? So you can get that where both of them are real, but they're not distinct. They're the exact same number. So this is overdamped. This is critically damped. So this is like perfect. It'll get there as fast as it can without kind of overshooting. So this is overshooting. This is underdamped. This is overdamped, and then like the absolute perfect thing would be, oh, you can't see any of that. So this is underdamped, overdamped, and then like critically damped is like the perfect scenario for us. We get there as fast as we can without overshooting. It's theoretical. You really can't achieve it because you're going to probably be slightly over or slightly under, and it's fine. So what you get here is you get X natural equal to AE to the S1T plus, this should be A1, and this should be A2, and this should be A1, and this should be A2. They're different constants. That's important. And so we can't just put E to the S2T here because they're the same thing. So what we do is we throw in a T. TE to the S2T. So that's the pattern for that one. And then the last case is imaginary numbers. So we would get something that looks like S1 is -2 plus 4, plus a J4, and then S2 would be a -2 minus a J4. This would be overdamped. The imaginary numbers should make you think sinusoidal, hence the reason you're going to get this like overshoot and then kind of come back underneath and then back up. So if it kind of springs back and forth, it is, underdamped. And you'll get the imaginary terms, which we saw with Euler's. And then there's a derivation for this, but I'm just going to skip to the end here. So it is E to the alpha t times the quantity. So you can call this A1 if you want. The derivation is actually going to call it A3, but it's not a big deal. Cosine beta t plus A2 sine beta t, close parentheses, where S is equal to alpha plus or minus beta, J beta. So our alpha is -2, and our betas are plus and minus 4. We drop the J out and we put those in. And you won't have any phase shifts or anything out of this form because it's just a quadratic. Okay? So our challenge becomes, with these, is really just finding which form of the natural response do we have so we can plug it in. Finding x particular, that's all the same stuff as first order. And for this chapter, x particular is going to zero out, so we actually don't even care. It's going to be 0 because we're going to be unforced. But just kind of a heads up. A lot of stuff from first order will carry over for that. Again, just kind of reviewing, standard form, second order, because it's linear. That's an x, not an x squared, x not an x squared, x not an x squared. We sub in, we get this form, which is a quadratic equation. Again, you can use the regular quadratic equation if you want, or a factor. You have three cases: overdamped, critically damped, and underdamped. Underdamped is your sinusoidal case. Critically damped would be kind of perfect, and overdamped will get there, but slowly. All right, hopefully this helps. If you have any questions, feel free to ask me.